Okay. Hi, everyone. My name is Jason Nance. I'm a data scientist at RTI International, and today I'm going to be introducing Godly, which is a Python library that we've developed to do use deep learning for text classification. So how many people in the audience have heard of Google's BERT model, not the Sesame Street character? Okay, we've got a few hands. Has anybody in the audience tried to use BERT for one of their own applied problems, not one of the? Okay, so we got a few. So you probably understand the pain that I'm about to describe. So let's say that you want to use a publicly released state-of-the-art deep learning model. It's open source, all the code's out there, you can go download it for a applied problem, not one of the benchmark problems that it was trained and evaluated on. So we decided to do that at RTI for one of our research projects. And let's say it's a binary classification problem, like does a movie review have positive sentiment or negative sentiment? So if you want to use Google's BERT to do that, I'm going to show you how much code it took us at least. So the first thing you need to do is write a data export script to put the data in the correct format. BERT has a really specific format that it wants the data. It's kind of obscure. That's informed by some of the benchmarks that it was developed to use. And so we're already at about 100 lines just putting our data in this very specific format. And then you'll find there's some shell commands that you're going to need to run to actually invoke the BERT model. And these are a fairly complicated environment that you need to set up for it. So we have another script to set up that environment. We have another script to run a giant Docker invocation to actually train the models, mount all the volumes and all the environment variables and all that stuff. So we have another script that we use to do that. And then once you have a trained model, you need to run prediction on another data set. So we have an entirely different shell script to do that, to run the trained model predict on another data set. And then finally, we want to know whether the model is actually any good. So we need to evaluate it. We have just a Jupyter notebook for that, just to generate some simple evaluation metrics. And so we're up to 187 lines of code just to run this one model and see if it works at all. And this doesn't even count, hours spent reading blog posts or the GitHub documentation or whatever else, trying to figure out how to get the code to work with Google's BERT model. So that's a ton of effort. And let's see how fast the state-of-the-art in deep learning is changing. And probably most of you already know the answer to this. So we're going to look at the DBpedia classification benchmark, how the best score on that has changed over time according to paperscode.com. So in 2015, there was a character-level convolutional neural network, was the best performer. 2016, Facebook released a strong baseline in their fast text model, and there was also a combined convolutional network and long short-term memory network. 2017, there were a couple new convolutional network architectures that advanced the state-of-the-art. 2018, ULMFit was released. 2019 has been a really big year. So Google released their BERT model, which was like a huge jump forward in the state of the art, and there have been other derivative models based on that architecture, including Microsoft's MPDNN and XLNet. So even multiple times per year, we're seeing an advancement in the state of the art. And if you want, the best model to work on your research problem, you're going to have to redo all that effort that I just showed in the previous slide all over again for a completely new model from a completely different research team. Potentially different libraries, different versions of PyTorch, TensorFlow, Chainer, whatever else they might be using. You're going to have to do it all over again. So, you might do all that work, and then it's no good to you 3 months down the road when a new model gets released. And so why does this happen? So if you're a methods researcher and you're one of those really clever people out there actually building these deep learning architectures, which I'm not, I just use them, you're incentivized to develop models that are the best. And the conventional way of determining what's the best model is how well does it perform on these benchmark problems. And so this is a screenshot here of the GLUE leaderboard, which is a kind of composite benchmark that comprises a bunch of different tasks. So if you're a researcher, you're going to write your code just to evaluate your model on the GLUE benchmark, which might include all the other tasks. But it doesn't really concern you as to how someone's going to actually use your model for an applied problem in research. There's no reason for you to care about that. So all of these models that come out, they're great. They have all their code. You can easily reproduce these benchmarks. But as far as taking it and applying it to something new, it can be very difficult. So that's where we landed with Godly. It took a ton of effort to use a state-of-the-art model. We recognized that we might have to put in all that effort all over again in a few months when there's a new state-of-the-art model. And we realized that there's really, it doesn't seem like it's going to change. As far as methods researchers are just going to keep releasing these models that aren't really intended to be generally applicable. So we built Godly to be an intermediary between a uniform input and output format, and a bunch of different state-of-the-art models. So you put your data into Gobbly in one single format, and you get output in one single format, but you can use it with a bunch of different models and with exactly the same view. So you could run it on Google's BERT, on a simpler model like Facebook fast text, and your code is very simple and it all looks about the same. So the high-level overview of how the library is designed to make this work, if we start at the top left, that's our users, that's you and me, whoever's using the library. There's a couple different ways that you can use it. We have a higher-level experiment API, is what we're calling it. This is for the really canned workflows. So like for a classification experiment, you probably have a data set that you're training on and a data set, an evaluation data set that you want to run predictions on. So if that's the case, you can use our experiment API and you'll get this experiment results thing back. It has a few sort of best effort evaluation properties that I'll get into a little later. If your needs are a little more custom, like maybe you have two data sets that you want to train on, or you want to use embeddings or something like that, we have a lower level API that's made up of what we're calling tasks. And you can use these to do more custom things. And the task API is based on our sort of Docker base abstraction layer. So we basically have a Docker container for each of these models that has all the dependencies and everything installed. So you don't have to worry about any of that. We just programmatically spin up these Docker containers basically whenever you want to train a model or do whatever else. So on top of kind of the models that we've implemented, we have some additional features that are potentially helpful for text classification and applied research problems. The first one is data augmentation. So if any of you are familiar with using deep learning for images, this has kind of been around for a while in that case. The idea is that labeling data is expensive, and so you probably don't have that many labeled observations, but it's always better to have more data. So if you can change the data that you do have in a way that preserves the labels, you can generate more data and help your model generalize from a smaller amount of labeled data. So with images, it often looks like you'll have your original image, maybe you crop it, maybe you rotate it, maybe you scale it, and it's still, you know, if it was a picture of a hot dog before, it's still a picture of a hot dog. But it allows your model to latch on to things that are common about a hot dog and not the way that it was rotated in that particular shot or whatever. So only recently has this idea been applied to text. Basically, the idea is to take an original document and then replace parts of it with things that are similar under the idea that it's probably going to be the same label that, or even if maybe it reads a little weird to a human reader, it's very clear that, you know, a machine messed with this. It's similar enough that it still matches the label, but it's different enough that your model learns not to overfit specific words or phrases. So Gobbly provides a few different methods to do this. You can use word2vec, all of them are based on basically masking out a portion of words and replacing them based on some similarity metric. So the first similarity that we use is word2vec. So you can use a word2vec model to calculate similarity for different words. You can replace words based on that. We also have an interface to WordNet. So this is a language ontology for lots of different words. You can find synonyms and hypernyms and hyponyms, and you can replace words based on that. We also allow replacement based on BERT's masked language model. So one of the pre-training tasks for BERT is actually they will give it a document and then hide a portion of words and ask the model to predict what each of these words are. So it learns, okay, these words are appropriate in these contexts. And we can kind of take advantage of that for data augmentation by doing the same thing, just giving it your labeled documents and masking out parts of them and asking the BERT model to replace what it thinks should go there. So theoretically, you'll get something that's a little different from what you had before, but it's still roughly the same because the BERT model understands language context. So this has been, we have some very simple, highly anecdotal benchmarks for this, but we have found from the IMDb sentiment classification data set, if we downsample to about 100 to 1,000 observations, we got an accuracy improvement of 17 to 18% just by using this data augmentation technique, no changes to the model or anything like that. So in our experience, that 100 to 1,000 range, that's like about as much data as people are willing to label on a small to medium-sized research project. So we think that's really beneficial if you're doing this kind of applied work to use that. Another smaller feature that we've added here just for convenience is what we're calling document windowing. So most of these state-of-the-art models, they end up transforming text into a big matrix and then doing a bunch of multiplications with it on the GPU. And if the text is too long, that matrix gets too big, it'll blow up your GPU, not literally. But so you can basically, the way they limit this is by having a max sequence length. And so the naive way to deal with that is just to cut off all your documents at the max sequence length. But you may be missing information, especially if your criteria is X mentioned somewhere in the article. If you cut off only the first 512 words in the article, you're not going to find X actually. So we just have some simple helpers to break up your documents into windows and then just pass those into any of our models like you would any of your original documents. And then we have some helpers to pool the output in terms of average, min, or maximum, just to get maybe potentially a better picture of what's in all of your data and not losing some of it. And again, anecdotally, with a similar benchmarks on the IMDb sentiment classification data set, we found about a 1% accuracy improvement just from this. And of course, that if all of your texts are really short, you probably don't need it, but if they're really long, it might help more. So just a discussion of some of the architecture trade-offs from the way we implemented Gobly. We use Docker for our base layer, so that makes it super cross-platform. You don't need to worry about, do I have an NVIDIA GPU? Can I install CUDA or whatever? Because our Docker images will take care of that for you. And you can theoretically, we haven't really tested it much on Windows, but theoretically it should run on Windows. We developed it on OS X, on Linux as well. And you don't have to worry about any of the dependencies, installing Python, anything like that. The downside for the Docker approach is that there's a lot of latency and overhead using Docker. So anytime we want to send some data to a container, we have to write it to disk and then mount it in the container. Anytime we get output, we have to read it back from disk from the container. So you wouldn't want to use Gobly for a real-time sort of operational model. It's really only for batch and analysis kind of use cases. On the flip side, we do implement support for Ray, which is a distributed computation library in Python. And this will allow you to do parallel or distributed training. If you have a cluster or even just a multi-GPU machine, you can easily train multiple models at once if you're doing hyperparameter, something that we support as well. But this is only for the experiment API, so not for the lower. We don't offer parallelization currently at the lower task level. So if you are convinced and you decide you might want to use Gobly, I just wanted to show some of the example results that you will get out of our experiment results object if you just have a simple classification workflow. So the first thing is some metrics. We just have some really simple best effort metrics that are applicable across a wide array of problems: F1 score, precision, recall, accuracy. And this, if you have any experience with Python, the bottom part probably looks really familiar. It's just the scikit-learn classification report. So this is just the default that we provide. I should note that for all of this experiment stuff, we have like a pretty printed, easily human readable version, but we also provide the computer readable JSON or whatever is appropriate. So if you have, if you want to run your AUC or generate raw curves or stuff like that, you have access to the raw predicted probabilities as well to do whatever custom stuff you want. We have a plot, a predicted probability plot that we'll generate for you as well. So this is a little complicated. This is for the 20 news groups data set. We have a row for each class in the data set, 20 different classes. The x-axis is the predicted probability of your model. It goes from 0 to 1. And all the different dots, the blue dots, are observations that don't belong to that class, and the orange dots are ones that do. So a perfect model would push all the blue dots all the way to the left, and all the orange dots all the way to the right. So this just gives you an idea of how well, or how the distribution of your model's predicted probabilities vary across all the different classes. So if there's a lot of noise in there, if the probabilities are kind of all over the place, you can tell that your model's not doing great with that class. But if it's mostly pushed to one side or the other, you can see, okay, it's pretty good at predicting that class. And this can help tell you, are there a few outliers that are driving down your evaluation metrics, or is it something sort of more systemic with certain classes in your data set? And the final thing here, sort of convenience option, is an errors report. So it can be really helpful to see where your model is really sure and where it's wrong. So for each class in your data set, we'll give you the false positives and false negatives that your model was most sure about, but it was wrong about. So in this instance, again, from the 20 news groups data set, the true class was about Microsoft Windows and miscellaneous, and the model was 97% sure that this was actually about science and medicine. You can see if you look in the text here, it talks about someone being a physiotherapist, clip arts of a skeleton, male or female body. So it's pretty clear why the model was unsure about that. And I don't know, maybe this observation is even misleading. So the benefit here is one, that you can just get an idea of what sort of things are tripping your model up. Maybe there's some pre-processing that you can do to help your model out if it's getting confused about certain things. The other thing is if you have potentially low quality labels, if your labeling task is difficult, you might find stuff that's been mislabeled. So then you can go and fix those labels and help your model out in the future. So we've found that that's helped a lot. Using this sort of process to find mislabeled observations helps a lot when we have sort of a fuzzy labeling task that even the humans aren't all that great at. It can really help to make that more consistent in terms of model. So where are we at? Where are we going? We released Gobbly open source on GitHub, so I have a link here. We've implemented several models, including Google's official BERT implementation, Microsoft's MTDNN, Google's Universal Sentence Encoder, or embedder, excuse me, and Facebook's fast text. We've also implemented an interface to the PyTorch transformers library by Hugging Face. So this also gives us XLNet, XLM, their PyTorch version of BERT, and Roberta. So all of these models are available to use in Gobbly, and they all look basically the same. If you want to try out something on BERT and then see if Roberta improves the results, you can do that. The other thing that I didn't mention here is we have a couple of really simple kind of trivial models. So just like a majority classifier, which one is the majority in the data set, and like a random embedder. So we found it can be a giant pain when you're writing code that uses these deep learning models to go back and you write it to use the output from the model, and the model trained all the way, but it did something you didn't expect, and the output format was different. You have to wait for the model to train all over again, and it really slows down your iteration. So we provided a couple of simple scaffold models. You can just write your code using these models and make sure the output structure matches your expectations, all the rest of your code works. And then you can go in and add the full, BERT, whatever, and use all your GPUs and do the full training with that model. So some things that we're looking to implement. So right now, we don't really support multi-label classification natively. It's just multi-class. So if you want multi-label, you have to train a bunch of 0-1, one versus rest models, basically. It would be nice if we could find a way to support multi-label. And we'd also, we've kind of stepped towards using Gobbly as a framework for the full text classification workflow, including pre-processing like data augmentation and stuff like that. So we'd like to include some helpers for downstream tasks using embeddings, potentially topic modeling, clustering, similarity calculations, anything that you might want to use embeddings for. And also some helpers for exploratory descriptive stats, so like word counts, distributions of labels, that sort of thing that might be helpful for you when you're using a data set for the first time. And of course, we'll be keeping an eye on the issues page in GitHub. If you find any bugs, if you have any feature requests, please post it on there. And we'll be watching and seeing if there's anything that we can easily implement to make it more useful for you all. So that's it. I've got my contact information here. Please feel free to reach out if you have any questions about the library. I'm happy to talk. Thank you.
So our second speaker today is Kristen Chen from WeStat, and she's going to talk about natural language processing.
So good morning, everyone. This is Kristen Chen. I'm currently the data scientist at WeStat. So today I'm presenting using natural language processing and machine learning to quickly classify open text field comments in a longitudinal study. So first off, I would like to acknowledge my co-workers, Catherine, Andy, Gonzalo, and John, who put significant contributions to this project too. Okay. So my talk will start from a background, and then the problem we try to solve, the data and methodology we use to solve the problem, and wrap up with a little bit of discussions at the end. So the open text field comments we're talking about here, it's from the Medical Expenditure Panel Study, MAPS. So the interviewer type comments to request updates or corrections to the data they collect earlier in the interview. So why interviewer leaves comments? First, MAPS asks respondent to record specific information about medical events over the last few months. So it's based on memory. So when the interview process to a certain point, it's very usual for the respondent to realize that, oh, they want to correct or add to some information that we collect earlier in the interview. And second, map is very large. So it has 1,200 questions, and you require 90 minutes to administrate it. So backing up to edit earlier response is very time consuming and can cause error. So to avoid backing up, our field interviewers can leave comments on the case field. So interviewer must select a category from a drop-out each time they enter the comment to facilitate data processing. So here I clarify two concepts. The first one is the comment, which is the data we have, and another one is the category, which indicate the broader topics of the comment itself. So we then need to process those comments. When the interviewer data are received by our home office, a team of 10 data quality control technicians need to review the comments for each case, and they have to determine whether or not it's correct category for the sentences, or whether or not we try to update the response. So this approach remains challenging because first of all, it's very costly to assess. First of all, comment itself is a test, and we need to review manually. And also, there's a large amount of the comments we receive in each data collection period. So for this period, we can receive like roughly 15K of comments. And also, we have to process those comments as soon as possible because MAP itself is a longitudinal study, means that the data have to go to the field in a very quick turnaround. So that's why it's natural for us to think, what if we can determine the correct category for the comments more quickly than the human being? So why identify the correct category for the comment is very important because it links to the correct standardized edit procedures for the technician to further process the comments. So it kind of serves as an entry point for us to process the comments. So we reframe everything I have just talked as a data science applicable problem. Can we use natural language process and machine learning to quickly classify the open text field comments with acceptable accuracy? So it means our computer go to suggest some categories for the comments, and the technician can choose the correct one based on that. So the data we have 4,400 comments for this case, which is labeled to 16 defined category. So the table you see here, the first column is the category we have, and the second column is sample comments we have. So we use comments to predict the category for the sentences. And the third column is the percentage of the comments in each category. So this table is actually started extending by the percentage. So you will see that we have like 22% comments for the first category, which is adding delete healthy care event. But we have like less than 1% for the last 4 categories. So this imbalance data adds difficulties for our modeling process. So the methodology. I will start to discuss our feature engineering, which including 11 features. We have 90 information items in text that we detect. And we have 2 metadata from the abbreviations of field names and question number from where the comment entered to the questionnaire. And on top of that, we have the text feature. So it's actually convert using a TF-IDF factorizer as a numerical matrix. So TF-IDF stands for term frequencies and inverse argument frequencies. And then I'm going to move to talk about our machine learning model. And finally, we deployed our model for production. So I put all the tools we use on the parentheses for each step. So for instance, for the large step model deployment, we're using Flask, Nginx, AngularJS for the front end, and the Docker containers. So feature engineering, as I say, we detect 9 key information items from the text. So it means, and then we build the features based on the detections. So it's actually based on a data exploratory analysis, and then we observe that the different combinations of the features we detect are associated with different categories. So if you look at the table, start from the second column, we detect date, expenditure, which symbolized as on the side there, zip code, telephone, respondents and their names. We detect some verbs and the synonyms, and we detect the provider, debt, and insurance in the sentences. So the reason why we did that is that, so if you look at the first row, for the comments about edit and delete medical provider information, it's very likely to contain a medical provider in the sentence. And the majority of medical provider information that the interviewer comment to edit or delete is about their telephone and the address, which is including the zip code. So by doing this, we are telling a model that if you see a zip code, a telephone, and a medical provider in the sentence, very likely that the category of these sentences is about adding, delete medical provider information. So another trick for this feature engineering is that we're telling a model to detect whenever there's a medical provider, regardless which specific medical provider in the sentence. So it prevents the situation that we have a new data comes in and it has a medical provider name that the model did not see in the training data, and it didn't pick up the information. So that's kind of the general idea about feature engineering, like you present the underlying patterns in the data and for the model to learn as informative as possible. So this kind of same idea is applied to other feature combinations that at least for each category that are listed in the table. And then I'm going to present some example comments to further illustrate my idea of feature engineering. So one of the example comments could be Nancy, patient ID 103, visited Dr. Grace Young on this today at this address and the telephone number and copay $50. So this comment is categorized as edit and delete medical provider information. So we definitely see date and expenditure and zip code and telephone and the name of the respondent and the medical provider in the sentences. So that's why when those information presented in the sentence, we call the corresponding features as 1, otherwise as 0. So that's why you're seeing that in the bottom table, we have those features and some is 0 and 1. Okay, so for the specific technique we use to detect the features, the first 4 we use regular expression, the names we use named entity recognitions, the verb we use thing set from what Western database building in the NLTK, and the provider drug insurance we match against 3 reference database. So the regular expressions and the name entity recognitions kind of self-explanatory. So I have to explain the ideas behind the verbs and providing drug insurance in the following slides. So as I say, we detect some verbs, including correct, change, add, and delete, and their synonyms from the sentence. So as you see, this second example, we have correct spelling of following prescriptions, and it's classified as add and delete prescriptive medicine. So we see a correct in the sentence. That's why we flag the verb and synonym features as well. Okay, so the reason why we did that, because if you look at the diagram at the bottom side, we're trying to capture 2 underlying actions in the commas, regardless the topics of the commas. So if you see, we have 16 categories of the commas, and you can classify as 2 actions. One is to the interviewer added a comma to add new information, and another one is to add it, delete, and change the existing information. So the category about add prescriptive medicines and add and delete prescriptive medicines are a perfect example that we are talking. They are the same topic but different actions. So if we just detect medicines or drug in the sentences, we are not able to distinguish between these two cases. So that's why we build this feature, and we expect that the interviewer will use those verbs, edit, delete, and change explicitly when they request to edit, delete, or change existing information. And this slide is about the feature engineering, like we build a feature about provider, drug, and insurance matching against, we have 3 reference databases. So we mainly solve 2 problems here. The first is lookup. We have very huge database of the 3 databases. So take an example for the provider, it's more than 1 gigabyte. The size is more than 1 gigabyte. We solve it as a text file in the local machine. So it took us 2 minutes to only just one lookup against the whole text file. So if we have 4,400 data points, it took us 6 days for just look up the medical provider database. It's definitely way too slow for production. So that's why we adopt a search engine called Elasticsearch, and then we reduce the processing time from 2 minutes to a few milliseconds for just one lookup. The second problem we have to solve is matching. So the provider, drug, and insurance are often written in different ways in the original commas and in reference database. So it means that we have to come up with an approach to first identify which parts in the commas to look up through the Elasticsearch. So obviously, we don't want to pass every single word in the sentence to the lookup because it's very unnecessary and inefficient. So we came out that we go to detect the null chunks from the comma because by nature, provider, drug, and insurers are not in the sentences. And also, after we got those results from the Elasticsearch, we have to verify the matching between the commas and the result. So we end up using fuzzy strength matchings based on the edit distance. So I'm using the commas you saw previously for this idea too. So we expect that our model understands Dr. Grace Young is a medical provider and then spread the features as one. Okay, so the null chunks we detect from the sentence is Dr. Grace Young, patient ID that you see in the table on your left hand. So those are very reasonable. If we pass through Dr. Grace Young to look up, and then we get Grace Chun Hong Yang from the database. So the idea is that if we're just using exact matching between these 2 strings, it's not going to match. Then if we use fuzzy strength matching, where they are matching even though we have doctor, which is a prefix in one string, and Chun Hong is an extra middle name on the other string. So the idea is that we're not able to use exact matchings to detect this feature. So we use fuzzy strength matching. So specific technique, we use syntactic dependence parsers from Spacey to detect the nouns. And we use fuzzy strength, the level span distance for the fuzzy strength matching. All right. So this slide is for text features, and I'm using another commas. It was not a hospital stay. Nancy visit a private clinic once a week on Mondays for allergies. So it's categorized as adding, delete, healthy bank details. So beside the 11 feature I just present on the previous slides, we also append the extra words from the sentences to the vector. So those words are hospital, stay, visit, private clinic, and by use after tokenized, and transforming using TF-IDF matrix. So for those who don't know TF-IDF, I'm pretty sure everybody knows it, but the idea is first, it's going to transfer the text into numbers, because the model only knows numbers. And the second idea is that it decreases the value of some words that appear very often in the documents, and then it increases the values of some rare words in the document because they are more informative for precision. So that's why you see allergy has higher value like 0.76 because we think it's the model itself think it's more informative. Okay, so this slide need to title as machine learning. So we have X, which is that we have one vector for one sentences, which step into a matrix, and we have Y, which is the category for each comment. Then we can move on the machine learning classification modeling. So what we have is we have 80% of data for training, 20% of data for testing. We explored two different models from Lasso, random forest, everything to XGBoost, and then we choose Lasso as our best option because it has highest accuracy. So for the model performance, we have 67% roughly for classification accuracy across 16 categories, which is not that promising. But when we look closer to the model, we see that we perform relatively worse for some cases that have for those minority cases. So that's why we propose that we show top 3 predictive category ranking by probability for each case, and then we cannot have 95% of accuracy of our testing data. So we also deploy our model for production. So on the screen, you see a demo after we export the model as a REST API, and then we build web applications for internal testing. So the idea is that you put the comma, field names, and question numbers for on the 3 open boxes on your left hand, and then you hit the submit, and those data is receiving by our API, and then passing the entire pipeline I presented previously from featurizing to prediction, and then the top 3 categories presented by our end user with their probability. So our technician can select one of them if they think they are correct, and then save the result. So this model is currently integrating with our DQC system, and then we try to present our end users with top 3 categories. So it will be real time, and we have it perform correctly 95% of the time because we have accuracy 94%. So I would say we kind of complete this task by simplifying the technician's life or making them choose 1 out of 50 or 3 rather than 1 out of 50. And it's definitely improving our entire data processing workflow for the comments. So that's it. Thank you so much.
Okay, our final speaker of this session is Rosa.